Hello, everyone. My name is Keegan Harris, and today I'll be telling you about our work on Bayesian persuasion for algorithmic recourse. So before I get started, I'd like to mention that this is joint work with my collaborators, Valerie, June, and Amit, as well as my advisors, Hoda and Stephen. So recent regulatory frameworks, such as the European Union's General Data Protection Regulation, motivate the need for forms of algorithmic transparency and explainability that are suitable for deployment in the real world. One form of transparency is to completely reveal the predictive model being used to the general public. However, this is often either infeasible or undesirable in many situations. For example, consider a bank which uses algorithmic tools as a part of their assessment for whether or not someone qualifies for a loan. Due to concerns about privacy or possible gaming of the predictive model, it may be infeasible for the full model to be revealed. On the other hand, one alternative form of explainability comes in the form of actions a decision subject may take in order to change the outcomes of machine learning models. To change the outcome of a machine learning model, a decision subject may take actions which will change his or her observable features. While there will be many actions the decision subject could take to receive a positive decision, some may be more desirable to the decision maker than others. For example, consider a person applying for a loan. A banking institution may prefer that the applicant pay off their existing debt before applying, as opposed to paying off little or no debt. But how can decision makers incentivize decision subjects to take good actions? If the decision maker recommends an action to the decision subject, how will they know it is in their best interest to follow the recommendation, given that the true model is unknown to them? So informally, we say that a decision maker's action recommendation is incentive compatible if it is in the decision subject's best interest to take the recommended action, given the information at his or her disposal. So in this work, our goal is to provide an alternative form of explainability in the form of action recommendations. And one question is the following: can we use these recommendations to incentivize socially desirable actions? And relatedly, what incentive do rational agents have to follow these action recommendations? Can we ensure that it's always in their best interest to do so? So in order to get a better understanding of why it might not always be a good idea to reveal the full model to the decision subject, consider the following example. Imagine a person applying to get a loan from a bank, and let's say this bank is very simplistic and only cares about the applicant's credit score when making the decision as to whether or not to give someone a loan. And for the sake of the example, let's assume that credit score is a good measure of creditworthiness and how likely it is that someone will repay a loan if given one. And to keep things simple, let's assume that the agent only has one action at his disposal, which is to pay off some existing debt, which will raise his credit score by 40 points. And this is desirable to the banking institute, regardless of whether or not the applicant is already qualified for the loan. But taking this action has some time or effort cost to the agent, so they would prefer to avoid doing so if possible. So now let's assume that the bank reveals the trained model to each applicant. In this setting, it's easy to see that the applicant will take the action to raise his credit score if it will help him achieve a desirable classification, and they will not take the action otherwise. So now let's consider the setting in which the decision maker does not reveal the model being used to the applicant and instead recommends an action to take, either pay off some debt or don't pay off any debt. Before training the model, both the bank and the applicant have some prior over how different levels of credit score will impact an applicant's ability to repay. And let's suppose the bank commits to the following signaling policy before training. If paying off debt, thereby raising their credit score, will push the applicant over the threshold for a positive decision, recommend that the applicant pay off their debt with probability 1. On the other hand, if it won't make a difference, recommend paying off debt with some probability p and not paying off debt with probability 1 minus p. And let's say that according to the prior, taking this action will help half the time and will not help half the time. In the bank, it's a utility of 1 when the applicant increases their credit score and utility 0 otherwise. So if the applicant were to follow the principal's recommendations, the principal would have expected utility of 1/2 of 1 plus p, where p is the probability that they recommend paying off debt when the applicant does not need to do so in order to receive a positive decision. And note that this is higher than the expected utility from the full revelation policy, where the principal reveals everything about the model to the applicant. And the cool takeaway here is that we can construct what this probability p should be in terms of the things like the prior and the cost of taking the action in order for the agent to be incentivized to follow the principal's recommendations. So in other words, we can pick P to ensure that the action recommendations are incentive compatible. So formally, we consider a setting in which a decision maker or principal wants to use a linear model to assign a label to a decision subject or agent based on a set of observable features. Before training the model, both the principal and the agent have some a priori belief about what the model will look like, represented in a figure as pi. So in other words, they have a prior over which observable features are important to the outcome being predicted. The principal then collects data and then uses it to train their model. After training their model, the principal recommends an action to the agent for a finite set of possible actions. This action recommendation is a function of the true model. Using this information, the agent can update their beliefs to form a posterior over the model, which they can then use when deciding whether or not to take an action or deciding which action to take. Finally, we say that the decision maker's action recommendations are incentive compatible if it is always in the decision maker's or decision subject's best interest to follow the recommendation according to their updated beliefs. And we call the decision maker's action recommendations across all possible models their signaling policy. So previously I showed an example of a signaling policy that's incentive compatible, but at this point you might be wondering how the decision maker should calculate the optimal signaling policy for an arbitrary number of different actions and observable features. In priori, this might seem near impossible, given that the decision rule generally belongs to some continuous space, and we would need to consider every possible realization of the decision rule when computing the optimal signaling policy. The key observation to make this computation feasible is that the space of all possible decision rules can be split into a finite number of regions, where the number of regions is related to the number of actions available to the agent. So in particular, each region is characterized by the set of actions which an agent can take to receive a positive decision if the true decision rule did end up lying in that region. And the principal can then signal based on what region the true decision rule ends up falling in without any loss of generality. Moreover, we can use this observation to characterize the principal's optimal signaling policy via the solution to a linear program where the number of variables in the linear program is proportional to the number of regions in the space of decision rules. So to recap, revealing the entire model being used to make decisions to the decision subject is often not a viable option. So alternative forms of explainability need to be explored. One alternative form of explainability is to recommend actions to decision subjects that would make them better off. Additionally, the principal can use these recommendations in her information advantage over the agent to recommend them to take socially desirable actions more often. While the computation of the principal's optimal signaling scheme initially appears infeasible due to the continuous nature of the set of all possible decision rules, we show that the problem of recovering the principal's optimal signaling mechanism for every decision rule can be reduced to the problem of finding the principal's optimal signaling mechanism for every region of the space of decision rules, of which there are finitely many regions, and this is without loss of generality. Using this characterization, we can then recover the principal's optimal signaling policy by solving a linear program. As far as directions for future work go, the number of variables in the linear program, and therefore the time it takes to solve the linear program, is proportional to the number of regions in the space of decision rules. In some settings, the number of regions is linear in the size of the problem, and by size of the problem, I mean number of actions and observable features. Whereas in other problem instances, this dependence can be exponential. So a tighter characterization of the runtime as a function of the size of the problem is desirable. Another important direction for future work is to provide bounds on the performance of the optimal signaling policy and characterize settings under which this persuasion mechanism can and cannot help. And finally, it would be nice to empirically evaluate our methods using a semi-synthetic experimental setup, such as one based on the Taiwan credit data set. So thank you for taking the time to listen to our talk. I'm happy to chat more if you'd like. And also feel free to come see us at the poster session. Thanks.